So my name's Darren Cook. I work for QQ Trend, which is a company that does everything to do with data. It's a small company, customers all over the world. So we do the mundane data stuff, finding data sources, repairing it, analyzing it, even screen scraping, that kind of thing. But then we go right through to the interesting, exotic stuff, the fun stuff. So we do a lot of NLP work, which is the topic of today's talk. You can see from my business card up there that we also work with a lot of Asian languages, difficult language pairs. We do a lot of data visualization, including VR work. So we're doing, this just shows some WebGL examples of interesting graphs, experimenting with what we can show the user, how much we can immerse the user in their data. And of course, we do a lot of machine learning and deep learning. As was just mentioned, I've written a couple of books. The first one for O'Reilly on low latency streaming to the browser using HTML5. Let me know if you'd like to have a look at the book. And hopefully some of you know this book. It's Practical Machine Learning with H2O. I'm just your typical working data scientist. When I started using H2O, I wanted to buy the book. It didn't exist. One thing led to another. I ended up writing it. OK. It came out last December or January time. It's had a lot of good reviews, excuse me, endorsements from some people I really respect, such as this guy. Got another one. Now, you notice this. Rupert Murdoch is holding a book this size. Rupert Murdoch must be really small. Either that, or the data is being distorted somehow. That's all I'm going to say about Rupert Murdoch. Let's move on. So I'm going to talk about NLP, and in particular, word embeddings. H2O recently has come with a word-to-vec implementation built in. In this talk, I'm going to show how it can be used for other languages. I'm going to show an example first in English, and then in Japanese, to give you a feel. What I'd like to do with this talk is train your intuition of when you should use word embeddings, when you shouldn't, what they're good for, and so on. I'm going to do the demo using the R API. The Python API is very similar. You can either ask me afterwards, or I will put the code up on a blog, hopefully by the end of the week, and I'll put both R and Python code there. So I'd like you to think of word embeddings as another type of dimension reduction. And when I say dimension, I mean each column in your training data, your inputs, is a dimension. Except in the case of categorical data where it's more than one dimension, which I'm going to come back to in a moment. So there's two main reasons we would do dimension reduction. The first is when we want to visualize our data. If we have 1,000 dimensions, we can't see that on the screen. Excuse me. So we reduce to 2 dimensions normally, possibly 3. If you use colors, you can get 4, but normally 2 dimensions. The other reason we reduce dimensions is to get a denser representation of our data. And obviously, the sparser our data is to start with, the more useful this is. Natural language data tends to be very sparse. I'll explain why in a moment. But a denser representation is quicker to train, takes up less memory, and is often easier for a deep learning network to learn from. Right. Just notice the spelling error. OK. These are the algorithms H2O provides for dimension reduction. So the first one, principal components analysis, is a mathematical technique using eigenvalues and other stuff I don't understand. It's not actually reducing dimensions. It's just rotating your data within those dimensions such that the first dimension has most of the information, and the second dimension has most of the remaining information, and the third has most of, and so on. And so by the time you get to the last few dimensions, there's not much information left, so you can generally throw them away. So in that sense, it's dimension reduction. GLRM, which I forget what it stands for, is very similar to PCA, but it allows you to work with more than just numeric data. And that comes built into H2O as well. The autoencoder is unsupervised deep learning. I'm not going to explain how that works. There is a book here that will explain it. But the key thing is your middle hidden layer, the number of neurons in that layer, is the number of dimensions you're reducing to. I'll come back to that in a moment. And word embeddings is dimension reduction. Just want to show this is MNIST data, handwritten digits. The left 6 columns, well, the leftmost column is the original. Then the next 6 columns are an autoencoder with 6 hidden neurons. So you can see that each of those columns is roughly the same amount of blur. So in an autoencoder, each of your dimensions is carrying an equal amount of the information. The right 6 columns are the first 6 principal components. If you look at the first of those columns, it's in the middle with a black background. You can see it's just a blur of the original source. The next one along looks like embossed version. By the time you get to the far right here, the character's getting quite hard to read. So there's not much information being left. And beyond 6 dimensions, perhaps you can safely throw it away and not lose much. I mentioned earlier, categorical data is not just a simple input. It's not a number. You can't feed it directly into a deep learning network. Now, I'm just using red, green, blue, pink as an example of a categorical column with 4 possible values. Internally, in your Python or R program, they probably have the numbers 1, 2, 3, 4. But you don't want to feed 1, 2, 3, 4 as a single input into your deep learning network, because pink is not 4 times red. It's not twice as much as green. They're distinct values. So what we do is we have 1 input neuron for each possible value. And when our input row is red, we put a 1 in the first input neuron, 0s in all the others. When it's green, it's 0, 1, 1, 0, and so on. So you only have 1 of your input neurons having signal, and all the others are 0. When we've only got 4 categories, this doesn't look too bad. But perhaps depending on if you're a graphic designer or not, or if you're a man or a woman, you might have a vocabulary of 20 colors or 100 colors. And 100 input neurons, your data is getting sparse. And sparse data is harder to learn from. When we're talking NLP, each word is 1 category. You can't say that cat is 3 times dog, or dog plus 1 even. So you end up with 50,000 input neurons for, say, a vocabulary of 50,000 words. And that's getting really, really hard to learn. And you're also losing the information that cat and dog are both animals and very different from the word to do, or it, or, I don't know, Spain. We're giving them all equal weight and throwing away a lot of information there. So word embeddings is the solution to that. Oh, yeah, let's skip over that. So I'm going to show a live demo in a moment in R, hopefully. The way word embeddings works is you take a large corpus of text data, and it looks for the surrounding context of the word. And if 2 different words tend to be in the same kind of context, and I'll show some concrete examples in a moment, then the idea is that they're similar in some way, either syntactically similar, so they have the same grammatical purpose, or semantically similar, so same meaning, similar meaning. And when I first heard about how well this was working, it was stunning. If anyone knows about word embeddings, you will have heard this example. But if you get the word vector for, say, king, and it's here in word vectors are often 100-dimensional or 300-dimensional space. King and queen will end up quite close because they're used in similar contexts, whether it's king-size bed, queen-size bed, or the king is in his castle, the queen is in her castle, and so on. And girl and boy will end up in similar places in that 300-dimensional space. But what's interesting is the vector from girl to boy will be very similar as the vector from queen to king. So you can start to do arithmetic and add words together and subtract words. So it's really grasping, even though it's just looking at how words are used in sentences, it's really starting to grasp their meaning. Okay, so see if I can type here. So I've brought in H2O. I'm defining a couple of helper functions, which I'm not going to go into, but you might notice I'm using principal components here. When I have more than 2 dimensions, I'm using PRCOM to reduce to 2 dimensions so that I can plot it. So here's my artificial, very artificial corpus. And I've used the same sentence structure in each sentence, and they just vary for the last 2 words. So the last but one column is a color, an adjective, and the last column is a type of vehicle. I've got, 3 cars, 4 lorries, a red Ferrari, because what other color would there be for a Ferrari, and a blue Mercedes. The first thing we need to do is tokenize the data. So to do that, we use H2O tokenize. So this command brings my data in from R into H2O. Then I need to convert it to a character, because by default, H2O will recognize string data as factors, categories. And then I tokenize it, and I give it a regex to tell it how to tokenize. And this one's just saying split on white space. Where am I up to? So let's run those. Tokenizing didn't take long. You can see what it looks like. It produces a single column where NA is used to separate the sentences. So NA marks the end of each sentence. I'm just going to grab that same list without the NAs for the purpose of visualizing the data later. And here is our word-to-vec call. So I pass in my single column data table, and I'm requesting just 2 dimensions this time. I don't have much data, 2 dimensions. We'll see how it does. It's easy to plot, at least. The last thing I'm changing, minimum word frequency, is 1. You shouldn't really do. It's just because I have a very small artificial data set. I don't want it to ignore anything. Generally, if you have a large corpus, 1,000,000 or 1,000,000,000 words, words that only occur once are usually typos or rare words, mistakes. They're going to be more likely noise. So we run that. It takes a second or 2. Word2vec is a fairly quick algorithm. And then the next 2 commands just allow me to visualize that data. So you can see, even with that simple example, we have some clustering. We've got the vehicles mostly along the top. And yellow and brown have come together. The other colors are further down. It's not great, but that was only 2 dimensions. So the next test will, excuse me, there we go. For the next one, I'm just going to go to 4 dimensions. And after that, I'm going to try 9 dimensions and increase the number of epochs, give it more training time. No. So that was Word2vec with 4 dimensions, and then using PCA to reduce it to 2 for visualization. Still doesn't look that great to me. It hasn't really found the clusters, has it? So let's try 9 dimensions. Maybe a bit of, all the colors are kind of, you could almost draw a circle around the colors now. But I think my problem here is my very small training data. I only have 9 sentences. So I'm just going to create a data set of 1,000, those same 9 sentences just randomly shuffled 1,000 times. So it's the same data, just more of it. Tokenize it. And let's use those, do those same 3 charts again with 2, 4. Has it gone yet? So I've lost track of where I'm up to. There we go. This time just with 2-dimensional data, but giving it more training data. You can see the colors are nicely on the left. The vehicles are in the upper right, and the grammar words are in the bottom right. So that worked quite well. Just try 4 dimensions. Still nice. And we don't really need to go to 9 dimensions, but 9 dimensions, and then displayed as 2, you can see we've got some really clear clustering there. It's nice. Okay. So let's try a different language. Does anyone here read Japanese? Nope. You'll just have to trust me then. So these are the same 9 example sentences. Almost. I'm saying, kore wa aoi kuruma desu. So this is a blue car, this is a red car, this is a green car, and so on. One fun bit of Japanese is the way adjectives are. There's 2 categories. So these ones end in this E character, and are called E adjectives. And then we have green ends in a no, the little circular symbol. And we have a couple of those. So we've got 2 different types. And of course, you notice the other challenge with Japanese is no spaces. So what I've done is I've tokenized it by hand. But your choice of tokenizer for Japanese is a difficult decision. In a project I hopefully have time to show you at the end, we end up writing and customizing our own tokenizers because it matters that much on a per application basis, really. Main thing I want you to notice from the tokenizing, it's one long list. I've added the NAs between the sentences, but no, the grammar particle, is a separate word, whereas the E adjectives, it's part of the word. And this is the way a normal Japanese tokenizer would work, so it's more realistic. Based on the previous example, I'm going straight to making 1,000 sentences. Hang on. Stop doing that. How do we get it? Right. So the difference now is we're no longer calling tokenize. I just import the data directly as a character column. And it's the same kind of data. We have each of the words with NA separating the sentences. The same training. And let's see how it looks. OK. This was using 1,000 sentences, and we're getting a very similar result. Wish I had a laser pointer. The E adjectives have all gone on the left. The 2 not adjectives are here clustered, with not in the middle, because I don't think it knows what to do with it. And the vehicles are all in the top right. So we're getting very similar clustering to the English. So you can see the similarities here, and the differences. On a per language basis, you need to tokenize differently, prepare the data differently, but then you can throw it into Word2Vec, and it will cluster it, whatever the language. We'll just try the 4. And the 9. Yeah, which is given a very nice split between each of the different categories. One thing I didn't point out is I kept the punctuation mark in deliberately. You will make this decision on an application-by-application basis. OK. So advanced considerations using word embeddings. If you go into the trouble of tokenizing, you'll also get POS, part of sentence information as well, whether it's a noun or a verb. In Japanese, what type of adjective it is, what type of verb. If it's a proper noun, perhaps even more detail, what type of proper noun. So it's possible to feed that into your word embeddings as well, which could be useful if you have the same word that's used syntactically differently, if the same word is a noun and a verb. You could feed in n-grams, so 2 or 3 words together. And compound words is low-hanging fruit. For instance, New York is a 2-word thing, but really it's 1 token. New York and New York are 3 distinct things. So detecting those compound words is much more trivial than that simple regex I showed you earlier. But for serious applications, it's worth trying to do. And then this is an either-or. Google make really large files based on really, really large data, like 6 billion word corpus, word embeddings in multiple languages. Or you could train your own. Word2Vec isn't too CPU intensive. So training your own each time is possible. The problem I found with the Google corpus is the decisions they've made on, well, what's on the next slide, actually. So I'll jump there. Do you want to remove certain stop words? Stop words in NLP are very common words, things like a, the, it. And if you're doing, say, sentiment analysis or gisting of a document, they tend to have low value. They get in the way because words like the crop up so many times in a document, they're not really telling you much. The same goes for punctuation. But if you're trying to generate text, then, which is an example I'm going to show in a moment of writing natural text, you want it to be able to write with all the words in the language. You want it to be able to say, the cat sat on the mat, and not just say, cat, mat. So it depends on your application of what words you want to throw away before you train. But on the other hand, lots of data is nice. So for some applications, the ready-made Google data can be nice. Okay. This is a project I've been working on. We've been working on in the company for a client. It's a startup, still in stealth mode, so I can't show you too much. But we're using LSTM's machine translation technology, all the NLP tips and tricks, to try and aid professional human translators to allow them to translate more quickly. So we're not trying to get rid of the translator completely, but we're seeing how much of the mundane, boring stuff we can help them with using all the latest deep learning technology. So we try and, they should never have to look something up in a dictionary again. We try and guess what dictionary lookups they're going to want to do in advance. And we're using the LSTMs and GPUs and all that fancy stuff to try and predict the next word they might want to type. So here, it's predicted including as the next word for the translation. And this is just an insight into the debug log. So these were the other words it thought it might suggest. This is based on some very toy training data, so not really a realistic example. But for this kind of example, you want to be training your own word embeddings, and you don't want stop words, and you want punctuation in there. You can see the third one is eh kind of punctuation. So, okay, that was basically what I had to say. I hope I've managed to train your intuition a bit on what word embeddings are and when to use them, their strengths and weaknesses, and if you're dealing with other languages, what things need the work of a data scientist or a language professional, and which bits can be treated just as you would treat English. Okay, thank you. Sorry?
We have questions that are going to come up.
Okay, do I have to do anything?
You don't have to do anything.
How do we collect the training data for non-English languages? Fundamentally the same way you'd collect it for English languages. If it's a specialist corpus, I will often ask my client to supply it. Because, and any specialist dictionaries, whether it's medical or finance industry and so on. Wikipedia is a good source. Read the license carefully, but generally you can use Wikipedia data. And if it's for personal use and you don't mind a bit of gray area fuzzy, you could just go out and screen scrape news websites and so on. But I didn't tell you that. This isn't on video. Can someone remind me what fast text is?
So it takes parts of the word. So like if you have Apple, it will also look up for AP,
Right.
PLE.
That's kind of the reverse of n-grams, isn't it?
Yes.
Going down to the character level. I haven't used it for embeddings. I have in LSTMs.
Okay.
A lot of LSTMs work at the character level. And for me, that seems a bit of a dumb idea. When you have a dictionary of words and you can tell it how the words are spelt. But on the other hand, it's amazing that it learns to spell words. It's working at the character level, but it strings together characters that are real English words. So, and it's a bit easier to write a character LSTM. So, yeah, but I haven't for embeddings, sorry. I think for that one, you would have to write your own regex. So the H2O tokenized function is fairly simple. If you can do it with a regex, you can do it. Otherwise, like I did with the Japanese, write your own pre-processed data in advance. The Python NLTK library is very strong for text processing. So that might be a better place to start if you have complex needs. It will go on my blog, which is darrendev.blogspot.com. Hope.
Spell that, and I can just post it for everyone to see.
Yes.
Give me just a second. You can continue answering the next question.
Yep. Why is the company called QQ Trend? We do a lot of work with finance industry. That's where the trend comes from. We algorithmic trading and trying to predict which trends are going to continue, which are going to change. And the QQ just came like, it has lots of positive connotations like quality, quantity, and so on. It's Darren, as spelt there, and then DEV, and then it's on Blogspot. Yeah. Did it work?
I'm just going to send it up to Slido so everyone can see it. There you go. Is that it?
That's it, yes. Yeah, it'll be there by the end of the week, I hope. Any more questions? No? Okay, thank you.